A man who never attended university wrote down the formulas that describe black holes, 40 years before anyone knew black holes existed. His name was Ramanujan, a self-taught Indian. He dreamed of mathematics and claimed that a goddess dictated the formulas to him. When he sent his notes to Cambridge, the mathematician Hardy almost threw the letter away, but something stopped him. He and a colleague spent the entire evening poring over those sheets. By nightfall, they both realized either this was the greatest hoax in the history of science, or they were witnessing a genius unmatched for a century. Ramanujan died at 32, in poverty, knowing nothing about quantum physics, string theory, or black holes. He simply wrote down what he saw inside his head. And then, decades later, physicists discovered these objects and discovered he already knew. How can this be explained? You could say it was a coincidence, but then you'd have to explain a whole bunch of coincidences in a row. Because Ramanujan's story is no exception. It's the rule. Mathematicians write equations again and again and discover things inside them they didn't expect. Things they later find in reality. This happened with Dirac, with Leverrier, with Higgs. And each time the same question arises, a quiet, almost uncomfortable one. What if mathematics doesn't describe reality? What if it is reality? In 1960, theoretical physicist Eugene Wigner wrote an essay with the ponderous academic title, The Unfathomable Effectiveness of Mathematics in the Natural Sciences. Behind this title lay a simple, almost childish question, one that scientists still have no reasonable answer to. Why does mathematics work at all? Think about this for a second. Mathematics is an abstraction. People invented it in their heads. Numbers, functions, geometric shapes. No one negotiated with nature. No one asked the universe whether it could be conveniently described through differential equations. And yet, it is described. More precisely, it is not simply described. It obeys, down to the last decimal place. Take Mercury's orbit. Newton calculated it using his equations and got a nearly exact result. But there was a tiny discrepancy. The orbit shifted slightly more than the theory predicted. For 2 centuries, this was dismissed as a measurement error, until, in 1915, Einstein wrote completely different equations, the equations of general relativity. Beautiful, elegant, derived from purely theoretical considerations about the nature of space and time. And they provided a precise answer, down to the last second of arc per year. Einstein didn't measure Mercury's orbit. He was thinking about geometry, and geometry knew the answer. Wigner couldn't explain it. He wrote it down. It's a miracle, and we have no right to understand it or deserve it. Science rarely uses the word miracle, but here it burst forth. And here's the catch. One could relax. Mathematics is simply a very convenient descriptive language. Like a map that isn't the terrain itself, but helps one navigate it. A convenient tool, nothing more. But tools don't predict what hasn't yet been discovered. Maps don't depict cities that haven't yet been built. And mathematics draws. Time and again, physicists wrote down equations, and from them, they derived objects they themselves didn't believe existed. Then they went to the lab, and they found them. This happens so often that it no longer surprised professionals. But if you stop and think about it, it should knock the wind out of your sails. The language people have created in their heads describes reality more accurately than any direct observation. It predicts the future. It points to the invisible. It knows what its creators do not. There are only 2 explanations. The first is an incredible coincidence that has lasted for 4 centuries. The second is far more disturbing. Mathematics works not because it's a convenient language for description, but because there's nothing to describe, because reality is mathematics. But if this is so, then what is the table at which you are sitting? What are your hands? What are you yourself? And why have physicists who study this very question begun to come up with answers that make you want to close your laptop and go outside for some fresh air? In 1928, A young British physicist sat over a piece of paper, trying to reconcile two equations that categorically refused to coexist. On the one hand, quantum mechanics, newly born and not yet fully understood. On the other, Einstein's theory of special relativity. Both described reality, both worked brilliantly, but they were incompatible with each other. Paul Dirac wasn't satisfied with this. He was one of those people for whom an ugly equation is physically unpleasant, much like a false note for a musician. And he started not with experiments, not with measurements, he started with aesthetics. An equation must be symmetrical, elegant, otherwise it's wrong. A few months later, he found what he was looking for. The Dirac equation, 4 lines of mathematical symbols, united quantum mechanics and relativity for the first time in history. Physicists gasped. It was beautiful. It worked. It described the behavior of the electron with incredible accuracy, but it had a side effect that left everyone baffled. The equation yielded 2 solutions. One was an ordinary electron with a negative charge. The second was something with the same mass, but a positive charge. A particle that didn't exist, that no one had ever seen, that, by all accounts of the time, couldn't exist in nature. For several years, Dirac didn't know what to make of this. At first, he assumed the second solution was simply a proton. Colleagues politely pointed out that this didn't work mathematically. Then he took a step few dared to take. He trusted the equation more than his own intuition. In 1931, Dirac wrote, "There must exist a particle, the mirror image of the electron, an antiparticle, antimatter." The physics community reacted to this with caution. Elegant, of course, but where is the evidence? You can't seriously claim that an entire class of matter exists just because an equation says so. A year passed. Carl Anderson was studying cosmic rays in California. In a cloud chamber, he saw a particle trace, just like an electron, but bent the other way. He didn't know about Dirac's prediction. He simply looked at the data. The particle behaved like an electron with a positive charge. Anderson named it a positron. Only later did he learn that the mathematician had already been expecting its appearance, a year earlier on a piece of paper, without any equipment. The equation was known before. This isn't the only such case. It's not even the most astonishing. In 1846, mathematicians Adams and Leverrier noticed that Uranus's orbit was slightly off from their calculated values. They solved the equations and pinpointed the spot in the sky where the unknown planet, whose gravity was distorting the orbit, must be. Astronomers pointed a telescope at the pinpointed location. Neptune was there, with an error of less than 1 degree. The planet wasn't searched for, it was identified. Or take the Higgs boson, a particle predicted in 1964 based on mathematical symmetry in the Standard Model. Peter Higgs deduced its existence from equations that would have been meaningless without it. For nearly half a century, physicists built accelerators, spent billions, searching for what mathematics had already promised. In 2012, they found it. Mathematics waited 48 years, and it turned out to be right. It's important to pause here and appreciate how strange this is. We're used to thinking that science works like this: first observation, then theory. First fact, then explanation. But time and again in physics, the opposite happens. First equation, then reality. A mathematician sits in silence, manipulating symbols on paper, and from them, extracts an object that later shows up in nature. As if the equation doesn't describe the world, as if it precedes it, or, worse, as if it is the world, and experimentalists are simply confirming what mathematics has known all along. Philosophers of science have coined a beautiful term for this phenomenon: unfounded prediction. A theory developed to explain one phenomenon suddenly accurately describes another, one its creators never even considered. This happens too often to be attributed to luck. But there's another interpretation, a more radical one. If mathematical structures don't simply describe physical objects, but precede them, perhaps physical objects are mathematical structures? Perhaps the positron existed in Dirac's equation Not as a prediction, but as a fact, people just weren't looking in the right direction yet. Dirac, by the way, thought along similar lines. At the end of his life, he said something that physicists still cite today. The beauty of equations is more important than their agreement with experiment. Because if an equation is truly beautiful, experiment will sooner or later confirm it. Nature cannot be ugly. It sounds mystical. But Dirac was one of the most rigorous and cold minds in the history of physics. He was serious. And here arises a question that physicists have long been hesitant to ask out loud. Okay, mathematics is precise. Okay, it predicts. But maybe that's simply because we have good models? Perhaps there's a boundary somewhere, a place where mathematics ends and real, raw, indescribable reality begins? Such a place was found. It's called the quantum world. And there, mathematics didn't just work, it demonstrated something that Einstein himself rejected for the rest of his life. Because what it demonstrated contradicted the most basic notion of what it means to exist. Imagine tossing a coin. While it's in the air, it's neither heads nor tails. It's both at once. But the moment you catch it and look at it, it becomes one thing. And not because you caught it, but precisely because you looked at it. Sounds absurd? That's exactly how reality works at the level of elementary particles. And this isn't a metaphor. It's the result of experiments replicated thousands of times in laboratories around the world. In 1927, physicists conducted an experiment that revolutionized everything. It's called the double slit, and in its simplicity of setup and profound consequences, it's unparalleled in the history of science. They use a screen with two narrow slits. Behind it is another screen that records the impact of particles. They fire electrons, one at a time, with long pauses between shots to prevent interactions between them. If the electron is a particle, it should pass through one slit. Two spots should appear on the rear screen, opposite each slit. But this does not happen. An interference pattern appears on the screen, alternating fringes, as if a wave were passing through both slits simultaneously. Hundreds of fringes instead of two spots. One electron, two slits, simultaneously. Physicists decided to cheat. They installed a detector, a device that records exactly which slit a particle flies through. Just watch. Can't stop it, can't change it, just record it. The interference pattern disappeared instantly. The electron began to behave like a normal particle, passing through one slit, leaving one spot. Observation changed the outcome. The very fact that someone was watching changed the particle's behavior. Niels Bohr, one of the fathers of quantum mechanics, uttered a phrase that has become canonical. Anyone who isn't shocked by quantum physics simply doesn't understand it. Werner Heisenberg went further and formulated the uncertainty principle. It's impossible to simultaneously know precisely the position of a particle and its velocity. Not because our instruments are imperfect, but because a particle doesn't simultaneously have both a precise position and a precise velocity. Both parameters become certain only at the moment of measurement. Before measurement, a particle exists in superposition, in all possible states at once. This isn't ignorance, it's the objective uncertainty of reality. Einstein hated this conclusion. He spent the last 30 years of his life trying to prove that quantum mechanics was incomplete, that behind it lay hidden variables, some deep-seated variables that determine everything in advance, but we just can't see them. He said, God doesn't play dice. Reality must exist independently of the observer. In 1964, Irish physicist John Bell found a way to test who was right. He derived a mathematical inequality. If hidden variables exist, experiments should yield results within certain limits. If not, the limits will be violated. Experiments were conducted. Limits were broken. Again and again with increasing precision until Alain Aspect's definitive experiments in the 1980s, which were awarded the Nobel Prize in 2022. There are no hidden parameters. Einstein lost. God, it seems, does play dice after all. But quantum mechanics has another surprise in store, perhaps the most disturbing of all. It's called quantum entanglement. Two electrons that interacted in the past remain bound at any distance. You measure the spin of one in Moscow, and at the same moment, the spin of the other, located in Tokyo, takes the opposite value. Not with a delay, instantly, faster than the speed of light. Einstein called this spooky action at a distance and refused to accept it. But experiments confirm that entanglement is real. Two particles separated in space remain, in some sense, a single object. The space between them is not a barrier. Perhaps space is not what it seems at all. And here mathematics does what it does best again. It describes all of this with absolute precision. The Schrödinger wave function, the equation that defines the superposition of all possible states of a particle, works flawlessly. Feynman's quantum electrodynamics yields predictions that match experiment to 10 decimal places. It is the most precise theory in the history of science. But here's the paradox. Mathematics describes the quantum world perfectly, and yet no one understands what exactly it describes. What is a wave function physically? What happens during a measurement? Where is the electron located between two observations? Physicists have counted more than a dozen different interpretations of quantum mechanics. Copenhagen, many worlds, relational, transactional. The mathematics are all the same, but what lies behind it, no one knows. Richard Feynman once said, "If you think you understand quantum mechanics, you don't." He wasn't saying this out of modesty. He knew it better than almost anyone who ever lived, and that's precisely why he said it. At this point, one could give up, say, the quantum world is strange, incomprehensible, and it's better to simply use the equations without asking unnecessary questions. That's exactly what most physicists did for decades. Put philosophy aside, count it all, and shut up. But some didn't remain silent, because behind the quantum weirdness, the contours of something greater were beginning to emerge. If reality exists only through observation, if before measurement there is only a mathematical wave function, not a specific physical object, then what is real? The wave function, or what it collapses into upon observation? What if the correct answer is the wave function? What if the mathematical description is the only reality and everything else is just the way it manifests itself to the observer? It sounds like a philosophical play on words, but this is precisely the question physics has been working toward for decades. And this is where a theory that, at first glance, seems completely unrelated to quantum physics comes in. A theory born from weather observations that has turned our notions of order and randomness upside down. Because even chaos, it turns out, obeys mathematics. And that changes everything. Winter 1961, Cambridge, Massachusetts. Meteorologist Edward Lorenz wants to repeat a computer weather simulation he ran the day before. To save time, he doesn't start over. He enters intermediate data from a printout of the previous run. He rounds numbers to 3 decimal places instead of 6. The difference is 1 part in 1,000, smaller than a speck of dust on the scale of the atmosphere. He goes for coffee. He returns an hour later and discovers that his forecast has completely diverged from the previous one. Not just slightly, completely. Two simulations, which began with almost identical conditions, describe completely different weather systems after several months of modeling time. Lorenz looked at the screen and realized something fundamental had just broken. Not in the software, but in the very concept of how the world works. Until this point, science had lived in a cozy Newtonian universe. The rules were simple. Know the initial conditions accurately enough, and you can predict the outcome accurately enough. A small error in the input yields a small error in the output. The world was predictable in principle, even if not always so in practice. Lorentz destroyed this confidence with 1,000th of a unit. What he discovered was called sensitivity to initial conditions. Some systems are designed in such a way that a tiny deviation at the beginning leads to colossal discrepancies in the future. This isn't because the system is broken or random. On the contrary, it is absolutely deterministic, with each subsequent step rigidly determined by the previous one. But because of the way these errors accumulate, long-term prediction is fundamentally impossible. This idea would later be dubbed the butterfly effect. The flapping of a butterfly's wings in Brazil could theoretically trigger a tornado in Texas. Lorenz himself coined this image in the title of his 1972 paper. It was both precise and poetic, a rare combination in scientific literature. But here's what's important and often forgotten. Lorenz's discovery isn't a discovery of randomness, it's a discovery of a special type of order. Because when he built a mathematical model of his atmospheric system and plotted the trajectories in state space, something unexpected appeared on the screen. The trajectories didn't fly off shapelessly in all directions. They curled into two loops, like butterfly wings or the figure eight, never intersecting, never repeating exactly, but always remaining within the same infinitely complex structure. This was called the Lorentz attractor, a strange attractor, and it turned out to be an object of incredible mathematical beauty, a fractal structure of infinite detail, contained within a finite volume of space. Chaos turned out not to be a lack of structure. Chaos turned out to be a structure of such complexity that it appears random to an observer with limited measurement accuracy. This discovery gave rise to an entire science, chaos theory or nonlinear dynamics. And the further researchers dug, the more they discovered the same astonishing fact. The mathematical structures that generate chaos are found everywhere. In the beating of a heart, in the fluctuations of animal populations, in water turbulence, in stock market dynamics, in the rhythms of brainwaves. Benoit Mandelbrot, a mathematician who fled Poland, worked at IBM, and didn't fit into any academic school, discovered that the British coastline has a fractal dimension, that clouds, mountains, blood vessels, and tree branches are all described by the same type of mathematical objects. In 1982, he published the book, Fractal Geometry of Nature, which revolutionized our understanding of how shapes are constructed in the world. Nature doesn't draw straight lines and perfect circles. It draws fractals, and fractals are mathematics. Concrete, formalized, computable. Consider for a second what this means. The shape of a coastal cliff, sculpted by the ocean over millions of years. The structure of a lung, nurtured by evolution over hundreds of millions of years. The pattern of a snowflake, formed in minutes as it falls through a cloud. They all obey the same mathematical principles. Evolution didn't know about fractals. The ocean didn't solve equations. The snowflake didn't read Mandelbrot, but they all turned out mathematical, as if nature had no other choice. And this is where chaos theory connects with what we discussed earlier. Quantum mechanics showed that on small scales, reality is obscenely mathematical. Chaos theory showed that on large scales, where one would think brute physical randomness should reign, a mathematical structure also prevails, just of a different kind. Everywhere you look, there's mathematics. In an electron, in planetary orbits, in the shape of a mountain range, in the rhythm of a heart, in a swirl of candle smoke. One might say, so what? Mathematics is a universal language. It describes everything because it is flexible enough. But mathematicians counter this. Not all mathematics describes nature. Most mathematical structures invented by humans have no relation to the physical world. From the vast space of possible mathematics, nature selects specific ones and clings to them with astonishing consistency. Why these ones? Why not others? Physicists had no answer to this question for a long time, until one person proposed an explanation so radical that most of his colleagues initially simply laughed. His name was Max Tegmark, and he said, "Nature doesn't choose mathematics. Nature is mathematics. All of it, completely, without a trace, including you." In 1998, a paper arrived at the Annals of Physics. Its title was simple, yet monstrously presumptuous. Is there an external physical reality independent of the human mind? The author was a 30-year-old Swedish-American physicist named Max Tegmark from MIT. The answer he proposed was, yes, there is, but it's not what you think. It's mathematics. The editors published it, colleagues read it. The reaction was divided into two distinct camps. The first said, this is profound and revolutionary. The second said, this is beautiful nonsense. The debate continues to this day. But before we understand what Tegmark said, we need to understand who he is, because that's important. Tegmark isn't some amateur philosopher who decided to ponder the nature of existence. He's one of the world's leading cosmologists. His work, mapping the cosmic microwave background radiation, the echo of the Big Bang, has been cited thousands of times. He's received NASA grants, collaborated with the planet's largest observatories, and built detailed models of the large-scale structure of the universe. He's a man with an impeccable scientific reputation. And he's the man who wrote what he wrote. His central argument is simple at first glance, so simple that it seems naive. But it is precisely this simplicity that constitutes its strength. Physicists have long recognized that our world is described by mathematical structures. Any physics textbook is essentially a set of equations. Mass, charge, spin, energy, all these are mathematical objects. When a physicist has completely described a system mathematically, they have described everything that can be described. Beyond the mathematical description, there remains no additional physical content, no substance, no matter that exists beyond the equations. Tegmark asked a simple question. If a mathematical description is complete and exhaustive, why postulate some separate physical reality behind it? Why say that equations describe the world when one could say that the equations are the world? This is called the mathematical universe hypothesis. It sounds like a play on words, but it has a strict formal content. Tegmark asserts, any mathematical structure that is self-consistent really exists. Not in someone's imagination, not as an abstraction, but as a physical reality. Our universe is one of these structures, the concrete mathematics that we are. This leads to something astonishing. If all self-consistent mathematical structures are real, then there exist universes with different constants, different laws of physics, different spatial dimensions, an infinite number of realities, each a mathematical structure. Tegmark calls this the level 4 multiverse, and this distinguishes his concept from other multiverses, which simply postulate many similar universes with the same laws. His multiverse is the space of all possible mathematics, and we live at one point in this space. Critics immediately attack from two sides. The first said, this is unfalsifiable. Other universes are fundamentally unobservable. Therefore, this is not science, but metaphysics. Tegmark responded, our universe, too, was unfalsifiable for a medieval astronomer. The limit of the observable is the limit of our instruments, not the limit of reality. The latter said, if everything exists, then the theory explains nothing. It makes no predictions. Tegmark countered, the theory explains the most fundamental fact, why something exists at all, rather than nothing, and why that something is mathematical. In 2014, he published The Mathematical Universe, and it reached beyond the academic audience. It was read not only by physicists, but also by programmers, philosophers, writers, and people who had never opened a textbook on quantum mechanics. Because behind the technical language lay a question that everyone has asked themselves at least once. What is reality really? Tegmark is honest in his book. He admits that his hypothesis may be wrong. He lists counter-arguments. He doesn't sell a ready-made answer. He invites a conversation. But he doesn't hide behind academic caution. He says it straight. I think this is true. I think we are mathematics. And here's the interesting part. Tegmark's conjecture didn't emerge out of nowhere. It stands on the shoulders of several decades of physics, each taking a small step in the same direction. Ramanujan showed that mathematics knows nature without learning. Dirac showed that equations predict reality before it's discovered. Quantum mechanics showed that before measurement, only the mathematical wave function exists. Chaos theories showed that even randomness is mathematically structured. Tegmark simply said out loud what physics had been working towards for 100 years, but was afraid to utter. But his idea has a corollary that stops many. If the world is mathematics, then what is matter? What is this table, this room, this body? If there's no physical basis behind the equations, what exactly are you touching when you touch the wall? Physicists began to explore the answer to this question long before Tegmark. And it's so counterintuitive that most people, upon hearing it, ask again, thinking they've misunderstood. They got it right. Matter simply doesn't exist. And this can be proven. Take the hardest object near you, a table, a wall, your own hand. The sensation of density, resistance, massiveness, it seems there is nothing more real, nothing more undeniable than a physical substance you can touch. Now here's a fact. An atom consists of a nucleus and electrons. The nucleus occupies approximately 100,000th of the atom's diameter. If an atom were the size of a stadium, the nucleus would be the size of a pea in the center of the field. The rest is empty space. The electrons are somewhere in the stands, and they are so tiny that they are impossible to even imagine on this scale. Your hand is almost entirely empty space. 99.9% is nothing. Less than 1/10% is matter. But that's not the strangest thing. Because when 20th century physicists began to figure out what this remaining matter was, they discovered that it didn't exist either, just in a different sense. In the 1920s, parallel to the scandals of quantum mechanics, another theory was emerging, quantum field theory. Its architects were Dirac, whom we've already met, Wolfgang Pauli, Werner Heisenberg, and later Richard Feynman and Steven Weinberg. It didn't describe particles, it described fields, and it changed the very question of what matter is. Imagine space filled with invisible fields, like infinite strings stretched in all directions. An electron field, a quark field, a photon field. They permeate the entire universe from edge to edge, existing at every point in space simultaneously. In a calm state, these fields are smooth, relaxed, and imperceptible. A particle is an excitation of a field, a local ripple, a tiny node of voltage that propagates across the field like a wave across water. An electron is not a tiny ball flying through space. An electron is a wave packet in an electron field. A photon is an excitation of an electromagnetic field. A quark is an excitation of a quark field. There are no particles. There are only fields and their excitations. This is called the standard model of particle physics. It was developed from the 1960s to 1970s by dozens of physicists, Sheldon Glashow, Abdus Salam, Steven Weinberg, Peter Higgs, and many others. To date, it is the most tested theory in the history of science. Its predictions have been confirmed with an accuracy that is difficult to comprehend, to the 10th decimal place. No other scientific theory has come close to such precision. And this theory says there is no matter. There are mathematical objects, quantum fields, and their interactions. But then why is the table hard? Why can't my hand pass through it? The answer is magnificent in its paradox. You can't walk through a table not because there's matter there. It's because the electromagnetic fields of the atoms in your hand and the atoms on the table repel each other. Their wave functions can't occupy the same space, according to the Pauli principle. Hardness isn't a property of matter. Hardness is the electromagnetic interaction between fields. What you call touch is the force interactions between mathematical structures. The sense of the reality of the physical world is a signal that your brain interprets as density. There is no solid substrate behind it, only fields, only mathematics. Feynman, explaining this to his students, liked to say, if aliens came and asked to describe humans in one sentence, the best answer would be atoms. Everything else is a consequence. But now we know that atoms are also a simplification. A more correct term would be excitations of quantum fields, or even more correct, mathematical structures interacting according to certain rules of symmetry. Symmetry is a whole other story, because it turns out that it's what rules everything. In 1915, German mathematician Emmy Noether proved a theorem that Einstein called the most significant creative achievement possible to humankind. Noether's theorem states that every continuous symmetry in a physical system corresponds to a conservation law. Time symmetry is the conservation of energy. Space symmetry is the conservation of momentum. Rotational symmetry is the conservation of angular momentum. The laws of physics aren't rules that nature decided to obey. They're mathematical consequences of symmetries. Symmetries of what? Mathematical structures that describe fields. The picture that emerges is astonishing. Dig deep into matter and you find atoms. Dig deeper and you find nuclei and electrons. Deeper still, quarks and gluons. Deeper still, quantum fields. And at the foundation of quantum fields are mathematical symmetries, transformation groups, and abstract structures. At each level, the familiar physical image dissolves and gives way to mathematics. And nowhere, at any level, does anything appear that could be called substance in the naive sense, something that simply is beyond description. In his book, Dreams of a Final Theory, Weinberg wrote about this with a frankness rare for a physicist. Physics is ultimately moving toward a point where everything will be explained through the mathematical principles of symmetry, and no physical image will be needed. Mathematics will no longer be a language of description. It will become the object itself. Tegmark read Weinberg, and he wondered, what if Weinberg is literally right? What if the final theory doesn't just use mathematics? It is mathematics. What if there's no difference between mathematical structure and physical reality because they're one and the same? If so, then our world is not the only one, because there are an infinite number of mathematical structures. And if each of them is real, then we live in one of an infinite number of universes, each with its own laws, each as real as ours. This isn't just a philosophical conclusion. It's a structure that Tegmark has built in detail, level after level, universe after universe. And when you begin to understand just how deep this rabbit hole goes, it becomes hard to breathe. There's a question people have been asking ever since they learned to ask questions. What lies beyond the horizon? First, it was a question about the Earth. What's there beyond the edge of the map? Then about the sky. What's there beyond the visible stars? Now, what's there beyond the observable universe? What lies beyond what we can even see? Most people assume one of two answers. Either there's simply more of the same, stars, galaxies, emptiness stretching off into infinity, or there's nothing there. The universe is finite, and there's no there beyond its edge. Both answers seem reasonable. Tegmark offers a third, and it destroys both of the previous ones at once. He doesn't propose a single universe and a void beyond it. He proposes a hierarchy of realities, 4 levels of the multiverse, each radically larger and stranger than the last. And each subsequent level isn't a fantasy, but a logical consequence of the physics we already accept. The first level is the closest to our intuition. Our observable universe has a horizon. The light emitted 13.8 billion years ago at the Big Bang has traveled a finite distance, approximately 46 billion light-years in each direction, accounting for the expansion of space. This is all we can observe in principle, the Hubble sphere. But there's no reason to think the universe ends at this boundary. If space is infinite, and modern cosmology offers no reason to believe otherwise, then there's still space beyond the horizon. With the same laws of physics, the same constants, it's just unobservable. There are other galaxies out there, other stars, perhaps other planets with beings looking up at their own skies and asking the same questions. If space is infinite, and if the initial conditions after the Big Bang were certainly diverse, then by the laws of combinatorics, there must be exact copies of our observable universe out there somewhere. And copies with slight differences. And copies where you made a different decision this morning. Infinite space with a finite number of quantum states means infinite repetition. This is the first level. It's already dizzying, but it's only the beginning. The second level arises from cosmological inflation. In the first fractions of a second after the Big Bang, the universe expanded at an incredible rate, faster than the speed of light. Most cosmologists today accept inflation as an established fact. It explains the flatness of space, the homogeneity of the cosmic microwave background, and the absence of magnetic monopoles. But inflation doesn't stop everywhere at once. It ends at different times at different points in space, and each point becomes a separate bubble, a separate universe. Our world is one such bubble. Surrounding it is an endless sea of other bubbles, expanding faster than the speed of light, fundamentally unreachable. And each bubble has its own values of fundamental constants, its own electron mass, its own gravitational force, its own speed of light. Most of these bubbles are uninhabitable. They contain no atoms, no stars, no complex structures, because most combinations of constants do not allow life. We live in a rare bubble where everything has worked out just right. This is the second level. It's beyond imagination. But Tegmark goes further. The third level is Hugh Everett's quantum multiverse. In 1957, a Princeton University graduate student wrote a dissertation which his advisor, John Wheeler, initially tried to soften, fearing Bohr's reaction. Everett proposed a radical interpretation of quantum mechanics. The wave function never collapses. With each quantum measurement, the universe branches. All possible outcomes are realized, each in its own branch. You toss a coin, one branch comes up heads, the other tails. Both branches are real. Both continue to exist. It's just that the observer in each branch sees only their own outcome. Trillions of quantum branchings occur every second in every cubic centimeter of space. The number of parallel realities grows faster than any number that can be written down. Everett earned his Ph.D., left physics, worked as a military analyst, and died in 1982, never having seen his idea become one of the most discussed in quantum physics. Today, the many worlds interpretation is accepted by many serious physicists, including Oxford's David Deutsch, who built a theory of quantum computation on it. But the fourth level, Tegmark's level, absorbs all the previous ones. And it's the only one where there are no arbitrary assumptions. The first three levels postulate the same laws of physics, just in different regions of space or in different quantum branches. Tegmark asks, why these particular laws? Why these particular equations? Why is space three-dimensional and not seven-dimensional? Why these particular constants, even if they vary from bubble to bubble? His answer, there is no cause. All self-consistent mathematical structures exist. Each of them is a real universe. Ours is one of them. The infinite space of all possible mathematics is complete reality. There is nothing else to exist, and nothing not to exist. This eliminates the question, why these particular laws? Because all laws exist. We observe these particular ones not because they were chosen, but because we would not have arisen under any other. This is the anthropic principle in its most radical form. Critics say it's unfalsifiable. Tegmark responds, and this is his strongest argument, that a theory that postulates only our universe requires an explanation of why the laws are the way they are. This adds information that requires justification. His theory adds nothing. It simply says that everything mathematically possible exists. This is no bolder statement than saying everything exists. It's less bold than saying only this exists. But this picture inevitably raises one question. If we are a mathematical structure in a sea of infinite mathematical structures, why do we see what we see? Why is our experience the way it is? Why 3 dimensions and not 7? Why color, sound, pain? The answer to this question doesn't lie in physics. It lies in biology, more precisely in evolution. And it's even more destructive to our understanding of reality than anything we've discussed so far. Because what you see right now isn't reality, it's an interface. And it has a specific reason for being the way it is, and not any other way. Open any app on your phone, tap the icon, the interface appears, buttons, colors, animation. You interact with it, it responds. It's convenient, clear, intuitive. But not a single button on the screen reveals what's going on inside. The transistors switching billions of times a second, the electrical charges, the binary code, the quantum effects in silicon lattices. The interface doesn't have to represent reality, it has to be user-friendly. Now the question, what if your eyes, your ears, your entire perception are also an interface? Not a window into reality, but a screen, specifically designed by evolution so you can survive, not so you can see the truth. This is not a metaphor or a philosophical provocation. It is a scientific hypothesis, and it has mathematical proof. Donald Hoffman, a cognitive scientist at the University of California, Irvine, has devoted decades to a single question. Do we see reality as it really is? In 2019, he published The Case Against Reality, presenting findings that challenge the basic assumption most people live with their entire lives. Hoffman began with evolutionary game theory. He constructed mathematical models of competing organisms. Some perceived reality accurately, others perceived only what was essential for survival. The question was simple: who would win the evolutionary race? The result was clear. Organisms primed for survival outperformed those primed for truth, always and under any conditions. Because accurately perceiving reality requires enormous computational resources. Evolution doesn't pay for unnecessary expenses. It pays only for what helps it survive and reproduce. Hoffman formulated this as a theorem and called it FBT, fitness beats truth. Fitness beats truth. Mathematically rigorous, without exception. What does this mean in practice? Your brain wasn't designed to see reality. It was designed so you could eat, survive, and reproduce. Everything else is a side effect. Take color. Physically, color doesn't exist. There are electromagnetic radiations of different wavelengths. A wavelength of 700 nanometers isn't red, it just is. Your brain creates the color red as a label, a mark, a convenient way to categorize different types of radiation. It works, it helps you navigate, but red exists nowhere except in your mind. It's the same with sound, with smell, with pain, with warmth. None of these are properties of the external world. All of these are constructs of your nervous system, translating physical signals into subjective experience. Hoffman goes further. He argues that even space and time are not fundamental properties of reality. They are interface elements, convenient coordinates the brain uses for navigation, but they do not reflect the deep structure of what truly exists. It sounds crazy, but look how it fits with physics. Quantum mechanics has long hinted that space-time is not fundamental. Entangled particles interact instantaneously at any distance. The space between them is not a barrier. Quantum gravity, the area where general relativity and quantum mechanics converge. In most approaches, space-time is not used as a fundamental object at all. It arises as an approximation, an effective description on large scales. In 1997, Juan Maldacena discovered what's called the ADS/CFT correspondence, a mathematical equivalence between a theory of gravity in the bulk of space and a quantum theory without gravity on its boundary. The bulk and the boundary describe the same physical reality using different mathematical languages. The spatial dimension literally emerges from a mathematics that lacks it. If space isn't fundamental, then everything we perceive as located in space isn't a fundamental description of reality. It's an interface on top of something else. Hoffman offers his own version of what lies beneath the interface. He calls it conscious agents, mathematical structures that interact with each other in ways we perceive as the physical world. His ontology is unusual and controversial, but his critique of perception is mathematically rigorous. And this is where Hoffman meets Tegmark. Tegmark says, reality is mathematics. Hoffman says, our interface with this reality is designed by evolution for survival, not truth. Together, they describe a picture in which we are mathematical structures using an evolutionarily designed interface to interact with other mathematical structures and never see the mathematics directly. We are inside the equation, and we have no access to the equation from behind the screen. But this picture raises a question that inevitably arises in anyone who thinks about it long enough. If our perception is an interface, if our body is a mathematical structure, if consciousness is an informational process above physics, then what is the self? Where in this picture is there room for the subject who experiences all of this? Neuroscientists have explored this issue from a different angle, and they've found something that makes you want to sit down and remain silent for a long time. In experiments that have become classic, they discovered that the brain makes a decision several seconds before a person is aware of it. A signal in the brain precedes conscious intention. Your sense of being in the process of making a decision is perhaps also an interface. A convenient story your brain tells itself after the decision has already been made at the neural level. Then who are you? Physics's answer to this question is one of the most disturbing and at the same time, one of the most liberating that science has ever discovered. Because if you are a mathematical structure, you have properties you may never have considered, and one of them directly concerns what happens when that structure stops working. In 2008, neuroscientist John Dylan Haynes of the Bernstein Institute in Berlin and his colleagues conducted an experiment that made headlines in scientific journals and sparked a wave of philosophical debate that continues to this day. Subjects were asked to press a button, left or right, at any time they chose. Their only task was to remember which letter was displayed on the screen at the moment they made their decision. This allowed them to capture the precise moment of conscious intention. At the same time, the scanner recorded brain activity. The result was discouraging. 7 seconds before the person became conscious of their decision, the scanner already knew which button they would press. The pattern of neural activity preceding conscious intention contained information about the choice. The brain made a decision before the person even thought they were making it. 7 seconds. This is not an error. This is not an artifact of the method. This is a reproducible result. Where was that which you call yourself during those 7 seconds? This question isn't rhetorical, it's fundamental, and physics approaches it from an unexpected angle, not through neurobiology, but through thermodynamics and information theory. In 2014, Max Tegmark published a paper with a provocative title, Consciousness as a State of Matter, not as a product of matter, not as a property of matter, as a state. Just like solids, liquids, and gases. Tegmark proposed calling it a perceptron state and described the mathematical conditions under which an information system transitions to this state. The idea wasn't entirely new. It was being developed in parallel by the Italian-American neuroscientist Giulio Tononi, one of the most influential theorists of consciousness of our time. His theory of integrated information, outlined in his 2012 book, Phi, posits that consciousness is integrated information, not just any information, but information that is processed by the system as a whole, not as a sum of its independent parts. Tononi introduced a mathematical measure, the Greek letter phi, or phi. This is the amount of integrated information in a system. The higher the phi, the greater the consciousness. A photocell has a phi close to 0. The human brain has a very high phi. In between, there's a continuous spectrum. This means that consciousness is not binary. There is no hard and fast line between consciousness and no consciousness. There are gradations. A thermostat has a tiny amount of consciousness. A mouse has more. A human being has even more. This is not a metaphor. It is a mathematically defined quantity. The implication is radical. If consciousness is integrated information, then it can exist in any system with sufficient complexity and integration. In a neural network, in a properly organized computer, perhaps even in some physical structures that we don't consider alive. Tegmark adds his own layer to this. If reality is a mathematical structure, and if consciousness is a certain type of informational organization within this structure, then consciousness is a substructure of the mathematical universe. Part of the equation is self-aware from within. The universe views itself through its observers. It's beautiful. But that's not all. Because if you are an information structure, then you have a precise mathematical description. Not approximate, not metaphorical, precise. Every thought, every memory, every personality trait is a configuration of information processes, a pattern, a structure, and structures obey different laws than matter. Matter decomposes. Structure can be reproduced. A melody doesn't disappear when a record ends. An algorithm doesn't die when a computer shuts down. A mathematical theorem doesn't cease to be true when the mathematician who proved it dies. If you are a pattern, then the question of what happens to you after the death of the body becomes a different question. Not where does the soul go, but what happens to the structure when its carrier is destroyed. Physicists are cautious about this topic. In his public presentations, Tegmark goes right up to this point and stops. He says, mathematical structures are eternal. The Pythagorean theorem was true before the Big Bang and will remain true after the heat death of the universe. If you are a mathematical structure, then in some sense you are also eternal. In what sense exactly is a question physics has not yet answered, but there is something she is already answering. Experiments in quantum mechanics have shown that information is not destroyed. This isn't just a principle, it's a theorem, proven within the framework of unitary quantum mechanics. Stephen Hawking proposed in the 1970s that black holes destroy information, and spent 3 decades arguing with colleagues before admitting he was wrong in 2004. Information is preserved. It can be scrambled beyond recognition, but not destroyed. If you are an information structure in a mathematical universe, and if information is not destroyed, then what exactly happens to your structure when your body dies physically? Tegmark again pauses before answering. But in the 4th level of the multiverse, where all mathematically possible structures exist, your pattern exists regardless of whether it's realized in a specific physical system. A mathematical structure doesn't need a physical medium to exist. It exists because it's mathematically possible. It's frightening and at the same time liberating. Because if you're not a body that thinks, but a pattern realized within a body, then your identity isn't tied to specific atoms. The atoms of your body are completely renewed every 7 years or so. You're not made up of the same particles you were 7 years ago. You're the same structure in a new substance. The ship of Theseus is easily solved. The ship is a form, not planks. You are a form, a mathematical form. And here comes the final question, the most important of all. Not physical, not mathematical, it's human. If we are equations, if matter doesn't exist, if space-time is an interface, if consciousness is an informational state within a mathematical structure, then what remains? What does it mean to live, to love, to lose, to choose, if mathematics is the only thing behind it all? This isn't a rhetorical question. It's a question whose answer determines everything else. And the answer is unexpected. Because mathematics doesn't abolish meaning, it explains it. There's a theorem that's 2,500 years old. The square of the hypotenuse is equal to the sum of the squares of the other two legs. Pythagoras proved it around 570 BC. Since then, empires, languages, religions, and civilizations have come and gone. Peoples have vanished without leaving names. Libraries have burned. Cities that seemed eternal have crumbled to dust. The theorem has not changed even a single symbol. It was true before Pythagoras existed. It will be true after the sun goes out. It is true at every point in the observable universe and, if Tegmark is right, in every mathematically possible universe out of an infinite number. It doesn't need to be maintained. It doesn't need to be remembered. It requires no medium. Mathematical truth exists outside of time. And if you are a mathematical structure, then part of you shares this property. Not metaphorically, literally. But before this becomes a consolation, we need to honestly face the destruction this idea is causing, because it is destroying so much, and pretending otherwise is selling a pretty picture instead of an honest conversation. If reality is mathematical, then the intuition of a special place for humans in the universe fails to stand up to scrutiny. There is no privileged vantage point, no center, no design aimed specifically at you. You are one of infinite mathematical structures in the infinite space of all possible mathematics. Statistically, nothing. Structurally, something very specific. But not chosen. It hurts. It would be dishonest to pretend it doesn't. But here's what happens next if you don't dwell on the pain. Physicist Richard Feynman once argued with an artist. The artist said that science kills the beauty of a flower by breaking it down into molecules and photons. Feynman replied, "I see a flower no less beautiful than you, but I also see the dance of the atoms within it and the questions it raises. Beauty doesn't diminish with understanding, it multiplies. The same thing happens with understanding the mathematical nature of reality. Yes, matter doesn't exist in the sense you're used to understanding it, but that doesn't make your experience any less real. On the contrary, pain is real, not because it contains some special non-biological substance, but because it is an information process with specific functional properties built into the mathematical structure that is you. Pain is part of an equation, and the equation doesn't become any less real just because we know it's an equation. Love is real. Neuroscientists might describe it as a cascade of oxytocin and dopamine. Physicists as a reorganization of information patterns in two conscious systems, and mathematicians as a change in the topology of connections. This doesn't negate love. It describes the mechanism through which the mathematical universe realizes one of its states. The state you call love exists. It is part of the mathematics of reality. The meaning is real. Here's the most unexpected thing. It's commonly assumed that if the universe is cold mathematics, then it has no meaning. Meaning requires intention, requires someone who creates meaning. If no one created the universe with a purpose, then there is no meaning, there are only processes. But this reasoning conceals a substitution. It assumes that meaning must come from without, that it must be imparted by someone external. Tegmark reverses this. In the mathematical universe, meaning is a property of sufficiently complex information structures generated by mathematics itself. Meaning emerges from within, not imparted from without. It requires no author. It is an emergent property of sufficient complexity. You create meaning yourself, not arbitrarily, not out of thin air, but through the interaction of your structure with other structures, through relationships, through memory, through choice. Even if this choice is determined at the level of physics, it is determined by your structure, and therefore it is yours. This aligns with what philosophers called existential responsibility, long before physics provided a mathematical foundation for it. Sartre said, "Existence precedes essence. First you are, then you determine that you are." Tegmark adds a layer. You are a mathematical structure, and therefore you have the freedom to determine the configuration of that structure through the choices you make. But the strangest discovery was saved for last, not by Tegmark, but by the history of science itself. Look at the trajectory of the last 4 centuries. Copernicus removed Earth from the center of the universe. Darwin removed humans from the center of biology. Freud removed reason from the center of the psyche. Every step felt like destruction. Every step felt like humiliation. Earth is not the center. Humans are not the crown. Consciousness is not the master of its own house. And each time this humiliation was followed by expansion. Earth turned out to be not the center, but part of an unimaginably more beautiful and complex system. Humanity turned out to be not the crown of creation, but a branch of an unimaginably rich tree of life. Consciousness turned out to be not sovereign, but part of an unimaginably profound informational process. Tegmark takes it a step further. You are not an observer of reality. You are a part of reality observing itself. A mathematical structure within which a substructure has emerged capable of asking questions about the mathematical structure. A universe that, through you, looks at itself and asks, "What am I?" This is not a humiliation. It is the most amazing thing that can be said about a person. Because from the entire infinity of mathematically possible universes, from the entire infinite space of structures, structures emerged capable of self-awareness, capable of wonder, capable of finding beauty in equations, capable of questioning the nature of reality, and through that question, making reality more complete. Ramanujan dreamed of formulas and didn't know they would describe black holes. Dirac wrote down an equation and didn't know he discovered antimatter. Tegmark wrote a paper that his colleagues considered crazy and doesn't know if it will turn out to be true. But they all did the same thing. They took mathematics, an abstraction that lives inside the human mind, and discovered that it described something real, over and over again, for no apparent reason, or for a very deep reason, the very reason that Wigner called a miracle. Mathematics works because we are made of it. We recognize it because we are part of it. The mind finds mathematics in nature because the mind is nature, looking at itself from within. The final question of this conversation isn't physical, it's personal. If you are a mathematical structure in a mathematical universe, and if mathematical truths are eternal, then what exactly do you choose to do with the configuration of your structure while it is active? What connections do you create with other structures? What patterns do you reinforce? What form does your equation take? Physics doesn't answer this question. It only shows that the question is real. That choice is real. That you are real.